Hey guys, welcome back. Mr. Marone here. So today we're going to shift our focus in the proof unit away from congruence and figures that we've looked at with our triangles, our angle pairs, and our quadrilaterals. And now we're going to shift towards looking at some similarity and some of the proofs that are around that. So today we're going to prove three different proofs. We're going to complete three different ones. They're a little bit lengthy, but we are going to complete that, and then the next video you'll see how these apply in regards to solving proportions. So the first one we're going to do is to prove what's called the side splitting theorem. Okay? And that tells us that if I have a parallel line that runs through a triangle and it's parallel to one of the sides of my triangle, that it splits the other two sides that are not going to, or that have intersected, into proportional parts. So we're going to do a bit of a two-column proof here, and I'm just going to kind of free flow write it, but at the same time it will be two-column. So the first thing they gave us is that DE is parallel to BC. Okay, so that's given there, and the nice part about it is that it gives us a couple angle pair relationships that we know right away. We can automatically say that angle ADE is congruent to angle DBC, these two right here, because they're corresponding. So those are corresponding angles. And on the same thing on the right-hand side, we can say that angle AED is congruent to angle ECB over here. And once again, by corresponding angles. So what we can do is we can use that to show triangle similarity. We would think back to our similarity options. We can say that triangle ADE is similar to the outer triangle ABC by angle-angle similarity, because we have two sets of congruent angles and we know we have this shared angle at the top. These are similar triangles. Okay? And what that tells us is that the side lengths are going to be proportional. So in this figure, the right hand or the left hand side of my small triangle AD compared to the length of the whole left hand side AB is going to be equal to AE, top half on the right hand side, over that whole thing AC. Okay, since we have proportional sides. And if we think about this, if we were to define what these are, AB is just a combination of AD and DB. Right, we're just adding our two segments over here and doing some segment addition. Same thing on that right hand side. AC is just equal to AE plus EC. And what we can do is substitute those in back over here. So this can become AD over AD plus DB. And on the right hand side I've got AE over AE plus AC. And at this point, let's take a look at cross multiplication here. Let's cross multiply these, and I end up with AD times the quantity AE plus AC. That equals AE times the quantity AD plus DB. Okay? And if we were to distribute that, you just write them next to each other, and I'll use the little dot to indicate multiplication, but we're going to distribute those, and I've got AD times AE plus AD times AC, and on the other side I have AE times AD plus AE times DB. Okay. And if you notice, we've got these two sets of matching multiplication happening here, AD times AE. So we can subtract AD times AE from both sides, and I'm left with AD times AC equals AE times DB. Okay. And if we think about this, if we reverse our distribution here, in order to get our equation here back into a proportion, if we think back up at the top here, AD times AC would mean that AD is on the top left and AC is on the bottom right. And then to get this over here, I could write it as AE over DB, and that is in fact what we were aiming to prove, that we've got my top piece here over my bottom piece is equal to my top piece over my bottom piece. And I'm just going to make one change here because I miswrote. It was right here. This should be an EC, and this should be an EC, and this should be an EC. So this becomes EC, and then we do in fact have what we were looking for. So sorry about that. Too many letters got me a little jumbled up. So we're going to move to our next proof here, which is to prove what's called the angle bisector theorem. So an angle bisector theorem says if I draw in an angle bisector into my triangle, that it's going to divide the opposite sides proportionally. Okay, so we're aiming to prove that this side over the other side is equal to the piece on the left-hand side of my dividing over the right-hand side, so that there's a relation between the left-hand side pieces and the right-hand side pieces. So that's our ultimate goal here when we do this proof. And in order to do this proof, this is going to be kind of a unique way to do this. We're going to first create an auxiliary line. If we think back to when we were proving with our triangles, we used auxiliary lines a lot. So what I'm going to do is draw in an auxiliary line through point A that's going to be parallel to that angle bisector BD. Okay, so first thing we're going to do is create an auxiliary line parallel to BD through point A. All right, and then what I'm going to do is I'm going to extend BC to meet the new line. And we're going to call that new point right here point E. Okay, so we know that this is parallel to this. We now have a bunch of stuff that we can use. Okay? The first thing we can say is that this angle right here, angle BAE, is congruent to this angle here, angle ABD, and that's by alternate interior angles. We also have this angle here, angle CBD, and that's congruent to this new angle, angle BEA, and those are corresponding. Okay, so I've got a bunch of stuff in here. And if we think about it, with an angle bisector, just off to the right over here, that tells us that ABD was congruent to angle DBC, right? That's what it means to be an angle bisector. So we can use our transitive property here and eventually say, since we've got, let me switch my order so we can see it better, CBD, I've got ABD over here on the left, I've got ABD over here. I've got CBD here on the right, I've got CBD here. So those two angles here and here are the same. So we can use the transitive property to say that angle BAE is congruent to angle BEA. We could also have said it using substitution, using a couple substitutions, but I think that's a good shortcut way using that transitive property. Now that we've got these angles being congruent here, this is huge because it tells us that we've got an isosceles triangle here with BEA as our triangle. So that allows us to say that triangle BEA is isosceles. And we've got base angles are congruent here. And that also is huge because it tells us that BE is equal to BA, that those two segments are congruent to each other. Okay? And if we think about our side splitting theorem we just proved, that tells me that EB over BC is equal to AD over DC. And we'll say by side splitting. Okay. And if we just use substitutions here, right here, we can take out EB or BE and replace it with BA or AB, and we finish it up by saying that AB over BC is equal to AD over DC. And that's exactly what we aim to prove. And this was by substitution. So that's our second proof. Now we've got these two theorems we can use. We've got our angle bisector theorem. We've also got our side splitter theorem. The other thing we're going to do, just to kind of finish this up, is take a look at the Pythagorean theorem, something you guys have used extensively prior to this class. But I want to look at just some stuff that we've got here that is kind of cool. So you've got this setup here, and our given is that we have a right triangle, ABC, and there's an altitude, a line drawn from a vertex straight down to create a perpendicular line on our hypotenuse. Okay, and we're aiming to prove the Pythagorean theorem. So what's really cool about this figure is I can actually redraw this with three triangles. And I'm going to put them all in the same orientation so that we can see them. So our smallest triangle, the one on the left, I'm going to call this number 1. I'll call the medium one number 2, and then our outside one will be number 3. So triangle number 1, with our right angle on the bottom, has D here. They've got this shared side, which we don't have a name for, and we've got A, and they gave us this angle up at the top. So that's triangle 1. Triangle 2, a little bit bigger, has a bottom side here of E, has a hypotenuse of B, and has a congruent angle down here. We'll put an open circle there. And we've got our right angle. And then we've got our big triangle, which I'm going to reorient so that it faces this way. And then we've got side A, we've got side B, and we've got side C. And we also have a dot angle up here and a circle angle here. So if you notice, as we work through this proof, it's kind of two steps. If you notice from our little triangle, our left-hand triangle, and our big triangle, we've got angle-angle similarity. We've got the shared angle at the top and then the shared right angle. So we can say that the left triangle is similar to the whole triangle by angle-angle similarity. Okay? And that means that I can actually set up a proportion. If we look closely at this, my hypotenuse over my hypotenuse, A over C, is equal to my left side over my right side, which is D over A. And if we cross multiply this, we get A squared equals CD. And we're going to come back to that. Now, if we use our right-hand triangle and our big triangle, those are similar by angle-angle. They both have the open dot and the right angle. So our right triangle is similar to our whole triangle by angle-angle similarity. Okay? And once again, setting up a proportion, that gives me B over C, hypotenuse over hypotenuse, equals leg over leg, E over B. And when I cross multiply, I have B squared equals EC. Okay? If we were to combine those equations, so this is, I've got A squared equals CD, and I've got B squared equals EC. If I were just to combine these, I have A squared plus B squared equals CD plus EC. And if you notice, I could then factor out a C here, and I've got A squared plus B squared equals C times D plus E. Here's where it makes it super, super cool. So if you notice up here with segment addition, we just looked at segment addition there. Segment C is created by D plus E. So what I can do is substitute D plus E out and put a C in. So I have A squared plus B squared equals C times C, which gives me A squared plus B squared equals C squared, which is what we were aiming to prove. So you've now seen 3 proofs. It was a lot of proving, and there was a lot of stuff in here. But it opens up a whole bunch of different things that we can do, which you're going to see in the next video. So take a look through the notes, take a look at the homework for this night, see what you can come up with using these and applying these, and we will look back at more of the application in the next video.